Hi everyone, I'm Danny Jiménez-Aguilar. I'm a postdoc at Tufts University, and in this talk I will discuss some interesting features in domain wall evolution. This will be based on this paper with José Juan Blanco Pillado and Oriol Pujolas, and also on some upcoming publications with José and Oriol, and also with Matt Ellie, Francesc Ferrer, Alberto García Martín Caro, and Juan Sebastián Balbuena Bermúdez. This is the outline. First of all, I will explain how these domain walls are formed in the early universe. In the first part of this talk, I will focus on 2 plus 1 dimensional walls. Then in section 2, I will explain how the Nambu-Goto action, which describes the effective dynamics of these objects, predicts catastrophic evolution. Then in section 3, I will show how the field theory evolution is also catastrophic in pretty much the same way. Then in section 4, I will consider the 3 plus 1 dimensional case. And finally, in section 5, I will conclude with some remarks. Domain walls are topological defects that could have been produced in the early universe as a consequence of a phase transition. And the picture is the following. We have a real scalar field phi, which initially sits at the bottom of this quadratic potential, but as the universe expands and cools down, the effective potential develops to minima. Now, spontaneous symmetry breaking occurs in the sense that the field has to choose whether it falls to the negative vacuum or the positive vacuum. This is the situation in a 2 plus 1 dimensional universe. Here the colors indicate the value of the scalar field. And as I said, initially the field starts out at phi equals 0, and we allow for some perturbations. Then, if we evolve this configuration under the influence of the double well potential, in some regions of space the field will choose the negative vacuum in blue, and in other regions it will choose the positive vacuum in red. Now, since the field has to be continuous, there must be some points in space where the field goes through the top of the potential, and these are these green string-like regions, and this is essentially what the domain walls are. Of course, here we're in 2 plus 1 dimensions, and therefore these are string-like objects, but in 3 plus 1 dimensions we would have closed walls. What we will argue in this talk is that the subsequent evolution of these walls is catastrophic. Of course, the domain walls are field theory objects, but we know that the field theory action reduces to the so-called Nambu-Goto action in the limit of low curvature and in the absence of internal modes. It turns out that the Nambu-Goto action predicts that the local curvature of the walls will diverge in a finite amount of time, even if we start out with perfectly smooth initial conditions. This is what I mean by catastrophic evolution. As we will see, this is closely related to the presence of cusps, which are points that move momentarily at the speed of light on the wall. As an example of this fact, consider this circular loop in the Nambu-Goto approach. Here the color indicates velocity, and blue means that the loop is static, and red will mean velocity is very close to the speed of light. In this case, the evolution is trivial, but I just want to point out that in this case, all the points on the string reach the speed of light simultaneously at the collapse time. So we may say that this catastrophic behavior happens globally, so to speak. But this is not the case if we consider a different shape, like this example. Again, if we release this loop from rest and evolve under the Nambu-Goto equation, as you can see here, there are isolated points that reach the speed of light. What happens is that a single cusp emerges at each of these tips, and immediately after, this cusp bifurcates into 2 other cusps, which are there for some finite range of time. And furthermore, they define this knot-like structure, which I will refer to as the swallowtail. Although this was the Nambu-Goto evolution, we will see that this also happens in field theory. We believe that this phenomenon could have very important consequences for black hole formation or gravitational waves, because this process is a mechanism by which the string concentrates energy to very small scales. Before I go on, I want to make a bit more precise the definition of the swallowtail. Consider this polynomial, which is labeled by these coefficients a, b, and c. This is said to have a double root r if both p of r and p prime of r vanish, in which case b and c can be parameterized in terms of a and r. And this defines a surface in ABC space, which looks like this. And this is simply a boundary between the regions corresponding to polynomials with 0, 2, and 4 roots. And this is the definition of the swallowtail surface. Here on the left, I'm showing some constant A slices of this surface. Now let's see how the Nambu-Goto action predicts the emergence of this swallowtail surface. Let capital X be the coordinates of the position of the string, and since we are in a 2 plus 1 dimensional universe, these coordinates depend on two worldsheet coordinates. The Nambu-Goto action is given by this, where gamma is the determinant of the worldsheet metric and mu is the energy per unit length of the string. Now we can vary this action with respect to the coordinates to get the equations of motion. And normally one works in the so-called conformal gauge, where we impose conformal flatness of the worldsheet metric, and we also make this choice for the 0 coordinates. In this case, the equation of motion becomes the wave equation, and we obtain these two gauge constraints. Here, dots are derivatives with respect to time, and primes are derivatives with respect to sigma, which is the second worldsheet coordinate. Now, from the second gauge constraint, one can see that sigma is proportional to the energy of the string, and on the other hand, from the first constraint, we see that the velocity of the string is perpendicular to the tangent vector at that point. The solution to the wave equation is a sum of left and right movers, A and B, and the gauge constraints can be shown to lead to this condition on A prime and B prime. So these A prime and B prime vectors must be unit vectors. Now we can take the time and sigma derivatives of the Nambu-Goto solution, and here I want you to know that if there is a point t star sigma star on the string worldsheet where A prime equals minus B prime, this means that the velocity of this point is the speed of light. Here we're making use of this condition. And furthermore, the tangent vector at that point vanishes. So this is the precise definition of a cusp. Now from these two expressions, x dot and x prime, you can see that we can find A prime and B prime as functions of sigma at the initial time from the initial shape and the initial velocity of the string. Furthermore, since A prime and B prime are unit vectors, this means that we can draw them on the surface of the unit radius cylinder. For instance, consider this initial configuration. We have two wiggles on a straight string which are approaching. And from this initial data, we can find A prime and B prime, and we can draw them here. So this red curve is A prime at the initial time as a function of sigma, and this purple curve is minus B prime. Now, as time goes on, since A prime is a function of sigma minus t, the red curve will go up and the purple curve will go down. This means that at some moment, these two curves will intersect at a single point. And now, since this means A prime equals minus B prime, this is translated into the presence of a cusp on the string, which is this point here. Now, if we wait a bit longer, or actually immediately after, these two curves will intersect at 2 points, meaning that the initial cusp has bifurcated into 2 different cusps. And you can see that this 2-point intersection will take place for a finite amount of time, for a while, meaning that these 2 secondary cusps remain there for this amount of time. So now we are in a position that we can describe what's the condition for the formation of these cusps. And you can see already from this description that this will happen if these arms of the A prime and B prime functions are sufficiently long. If these arms were short, these two curves would not intersect, and therefore we wouldn't have any cusp. You can also see from here that what determines the length of these arms is this point here, or this point here in the case of B prime. And these are related to the vanishing of the second derivatives of A and B. We can make this more precise here. Consider again the initial configuration. The initial time, we will refer to this shape as psi, which is a function of y. And now let y1, y2, y3, and y4 be the locations on the y-axis of the inflection points of the string. So as you see, these are the points where the second derivatives of A and B vanish. So now the condition for cusp formation is that the product of the slopes of the string at y1 and y4 be greater than 1, and likewise for y2 and y3. If this happens, or both of them happen, then a cusp will emerge because the arms of A prime and B prime are sufficiently long, and this will lead to the formation of the swallowtail. Here's a representation of the string wall sheet. Time goes in this direction. So the initial configuration is shown here. We have the 2 wiggles here. Then they meet at y = 0, and then they pass through one another. If we zoom in this region, we would see something like this. This is not exactly the swallowtail surface, but it is closely related to it, and we can see this by taking the Navier-Goto solution and simply we now simply perform a Taylor expansion around the initial cusp. And one can see after some redefinitions that the coordinates y and z defined this way match perfectly the parametrization of the true swallowtail surface. One can also compute the curvature of a string as a second derivative of x with respect to y, and one can see that this is proportional to 1/t, and this t is sometimes measured with respect to the time corresponding to the initial cusp. So this is 0 at the event of the cusp, so the curvature truly diverges at these events. Now let's see what is the field theory evolution of this configuration. So here the colors again are the values of the scalar field, and the black curve is the solution to the Navier-Goto equation. The first thing I want to point out here is that, as you can see, the Navier-Goto action closely resembles what the field theory action dictates. In particular, we see that in field theory, we also have this cusp formation and swallowtail emergence. In this case, the amplitude of the wiggles was big enough for a loop to be ejected from the string. Let me play it again. So here we have this loop, which becomes some kind of oscillon, which later reattaches to the string. And I should say here that this was already observed for the case of global strings for by Emilia and collaborators. But the point I want to make here is that these extreme events lead to a huge amount of energy from the string. Now let's move on to the case of 3 + 1 dimensions. And we will see that this kind of catastrophic evolution also takes place in this case. So here we have the Nambu-Otto equation again. In the case of strings, the string wall sheet metric is a 2x2 symmetric matrix. And so in order to completely fix the gauge, we only need 3 conditions. In the case of 3 + 1 dimensional walls, this metric is a 3x3 symmetric matrix, and so we need 6 conditions to completely fix the gauge. As before, we will make this choice for the 0 coordinates, but now instead of imposing conformal flatness of the metric, we will just impose a diagonal metric. In the case of strings, these are 3 conditions, so the gauge is completely fixed. But now note that these are only 4 conditions, not 6. But this is convenient because now we can use the remaining freedom to parameterize the wall like this. And here I'm just focusing on cylindrical symmetry for simplicity. But now we can use all this information to derive the equations of motion. First of all, the alpha = 0 equation turns out to be a conservation law. And we can use this in the alpha = 1, 2, 3 equations, which translate into this system of coupled equations. Now we can solve this numerically. For instance, for this ellipsoid, which we release at rest. And this is the Nambu-Otto evolution in this case. In this case, we have a cusp emerging from each of these poles. And immediately after, it becomes a circle of cusps here and here. Here's another example, in this case for a pancake-shaped domain wall. And in this case, we see that the swallowtail emerges along the equator. Finally, this is the field theory evolution. This is just a 2-dimensional slice of the 3-dimensional ellipsoid. Again, the colors are the value of the scalar field, and the black curve is the prediction of the Nambu-Otto action. So with this example, we conclude that field theory evolution is also catastrophic. And with this, I come to my conclusions, which are basically 3. The first one is that the Nambu-Otto action, the effective description of the dynamics of the walls, predicts the local divergence of the curvature of the walls. And this happens in a generic way, even for perfectly smooth initial conditions. We have seen that this happens also in field theory, so the true field theory evolution of the walls is also catastrophic. And this happens both in 2 + 1 dimensions and 3 + 1 dimensions. And finally, we think that this is an important phenomenon because it concentrates energy into very small scales, meaning that this could have influence on black hole formation and gravitational wave emission during domain wall collapse in the early universe. And that's it. Thank you so much for your attention.